Hello everyone. So today we are going to do some numerical based on Routh hurwitz stability criteria. So we are going to do some problem based on theory we studied till now, like how to determine stability, how to find out unstable system using Routh hurwitz criteria. We also see special cases, one as 0 as the first element and also 0 in the entire row. Now, so we started with basic problem, how to determine the stability of system. So to determine the stability of system whose characteristic equation is s to the power 4 plus s to the power cube plus 8s square plus 4s plus 3 is equals to 0. Also comment on the location of roots of the system. So this is our characteristic equation. For now, for the characteristic equation, the Routh array will be, so we take first s to the power 4, then s to the power 3. Now s to the power 4 is 1, first coefficient is 1, then alternative it is 8, then 3. Okay, and for s to the power cube, so s cube is coefficient is 2, then 4, then 0. So we saw that this term comes from multiplying these. First we will multiply these two minus these two divided by this factor. So we can do this way, minus 1 by 2 and then take determinant of 1, 2, 8, 4. Okay, so what we are doing basically is, this is an, this is an minus this is an minus 2, this is an minus 3, this is an minus 1, this is an minus 3. Okay, so what we are doing is an into an minus 3 minus an minus 2 an minus 1 by an minus 1, and this minus sign is there, so it is minus, so this will become positive. So basically if I put the values, it is minus an is my 1 into 4, then plus 2 into 8 divided by 2. So it is minus 4 plus 16 divided by 2, that is 12 by 2. So I will get 6. So there is no sign change. So similarly we do for 1, 2, 3 and 0. It will be like 1, 2, 3, 0. This is minus 1 by 2. So if you will solve again, it is minus 1 by 2. It is 1 into 0 is 0. Then minus 6. So minus minus will become plus. So 6 divided by 2 is 3. So this is 3. So s to the power 1. So similarly we have similar way, 6 into 4 minus 3 into 2 divided by this 6 will give me s to the power minus 1, and s to the power 0 is again 3 into 3. This is 0. It will be 0. So it will be at the end again 3. So just let's write the first column only. So I will just erase it. So this is my first column elements. So first column is positive 1, positive 2, positive 6, positive 3, positive 3. So the signs are positive. So all are positive. So there is no sign change. So we can say system is stable. All roots lie in left hand plane, hence the system is stable. No sign change means system is stable, as well as since no sign change is there means all the root lies on left hand plane. Okay. Problem we are going to do on how to find out system is unstable or not. So the second problem will be, so using Routh-Hurwitz criteria. So RH means Routh-Hurwitz. Find the stability of system with characteristic equation s to the power 5 plus s to the power 4 plus 3s to the power cube plus 9 square s square plus 16s plus 10 is equals to 0. So the Routh array for the given system is the first s to the power 5. Okay, then s to the power 4, s to the power 3, to s to the power s naught. So here coefficient of s to the power 5 is 1, alternative it is 3, then 16, then for s to the power 4 it is 1, then 9, then 10. So I mentioned all the coefficients. So now this will be 1 into 3, 3 minus 9 divided by 3. So it will be minus 6 by, sorry, it's 1, not 3, it's 1 by 1. So it is minus 6. Similarly, 1 into 16, 16 minus 10 divided by 1 is 6. Okay, again similarly we will calculate minus 6 into 9, that is minus 54, minus 6 divided by minus 6, so it is minus 60 by minus 6. If it cancels, it is 10. Similarly, minus 6 by 10, this is 0, and divided by minus 6 will give me 10. So likewise I have calculated all the terms. Now for the first column is 1, 1, then minus 6, then 10, 12, 10. So positive, positive, negative, then there are 3 positive. So here are 2 sign change. One is from positive to negative, then negative to positive. Yeah. So we learn that number of sign change is equals to number of roots in right hand plane. So number of root on right hand plane in this system is 2, and the system is unstable. Now we can solve a problem if the first element of row is 0. Okay, so let's consider the characteristic equation of system s to the power 5 plus s to the power 4 plus 2s cube plus 2s square plus 3s plus 5 is equals to 0. Now the Routh array, so the first will be 1. The first coefficient s to the power 5 is 1, then alternatively 2, 3, so I put them, then I am having 1, 2 and 5, I put those values also. Okay, since if you will calculate, this is 2 minus 2, 1 into 2 is 2, minus 2 will be 0, so this term is here 0. Similarly, this is 3 minus 5 divided by 1 is minus 2. Okay, so this term here is 0. So we see that this term is becoming 0. So what we learned is we replace it by a positive number epsilon, small positive number. So 0 is replaced by small positive number epsilon now. So this will be epsilon. Okay, so now calculate another term. This will be 2 epsilon plus 2 divided by epsilon. Similarly, you calculate here 5 epsilon into 5 divided by epsilon is 5 itself. Now next you multiply these terms, minus this divided by this, you will get this term. Okay, so similarly you just do the calculation. So what we are doing over here, we are replacing small positive number epsilon 0 with small positive number epsilon. Okay, so what we do is we consider these terms, we check the signs now. So epsilon is small positive, so this is positive which is tending to 0, so its sign is positive. But in this case, if you will see 2 epsilon plus 2 by epsilon, if I consider 2, it will be 2 plus epsilon. So this is greater than 0 and this is also greater than 0. So this is positive number. Okay. Now another term, if I take the limit of this, when epsilon is approaching 0, so this will be 0, this will be 0, this will be 0. So this will be minus 4 by 2, which is minus 2, negative sign. Then this is again 5, positive. Okay, so now if we consider, I will just clear all. If we consider first column, it is 1 positive, then second is positive, third is epsilon, we assume epsilon is small positive quantity, so this is positive, this is also we found is positive. Now this quantity we found is negative, and finally 5 is positive. Okay, so we are having 2 sign change. Okay, so I will just do the calculations over here again. I'm just replacing them and I just written all the calculation which we have calculated earlier, how it's negative, how it's positive. I'm just showing that. Okay, so there are 2 sign change here. So number of roots on right hand plane is 2, and so the system is unstable. My system over here is unstable system. Okay, so let's consider one example where entire row is 0. So how we use the auxiliary polynomial and find out the roots and determine the stability of system. Okay, so let's the characteristic equation be given by s to the power 6 plus 3s to the power 5 plus 5s to the power 4 plus 9s to the power cube, means s cube plus 8s square plus 6s plus 4 is equals to 0. So the construction of Routh array, s to the power 6, then s to the power 5, then s to the power 4, then s to the power 3, then s to the power 2, and then so on till s to the power naught, s naught. So now first is 1, then it's 5, then it's 8, then it's 4, and here first is 3, then 9, then 6. Okay, so now for s to the power 4, we can calculate it as this is 15 minus 9 divided by 3 will give me 2. Then 24 minus 6 divided by 3 will give me 6. Then again here it is 18 minus 18 is 0. 12 minus 12 is 0. So I get here 0. So what we learn, we consider auxiliary equation. If this entire row is 0, we will consider auxiliary equation AS, and we go to the immediately upper row. To this 0 row, we will go to the immediately upper row. So what is that? S to the power 4. Here it is s to the power 2. Here it is s to the power naught, s naught. So I'm just writing auxiliary polynomial. Okay, which is equals to 0. So we take common as 2. So divide all the other terms with 2. and we get this polynomial equation. So what we do now is we find derivative of auxiliary equation, that is dAs by ds. With respect to ds, we are differentiating our auxiliary equation. So it will be 4s to the power cube 6s is equals to 0. So the coefficient here will replace these zeros. Okay. Now this is 4, this is 6. So s to the power 2 will be 3, this will be 4. Now it is 18 minus 16. So it will be 2 by 3 and it is 4. So just consider the first column. There is no sign change. So all the terms are positive. Positive, 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 positive. So there is no sign change. That means there is no root in the right hand plane. But we can't, for determining the stability of system, we need to find out the root of auxiliary equation, because we learned that root of auxiliary equation is also the root of characteristic equation. So the root will determine the stability. So here we see that s square plus 1, we just solve this equation. So it is s square plus 1, s square plus 2 is equals to 0. So s square plus 1 is equals to 0 and s square plus 2 is equals to 0. Okay, which will gives me these 4 roots of my characteristic equation. So there are 4 roots of auxiliary, 4 roots are on imaginary axis. So if we construct, we just draw the S plane, and this is sigma, this is j omega, as this is j, okay, it should be 2, it should not be, it should be root 2. Over here it's little mistake, so you just consider it root 2. Okay, here also it will be on root 2, means 1.14. okay, 41. Okay, so these all roots are on imaginary axis, but none are repeated, so the system is marginally stable. So some problem on feedback. Now we do some problem on determining the gain of the feedback system, what we learned in lecture of Routh-Hurwitz criteria. So how we can, or we will see how we can use Routh-Hurwitz criterion, apply it in feedback system to determine the gain. So quickly we will do that also. Okay, so this is also clear that why it is marginally stable, because all the roots of characteristic equation of auxiliary equations are imaginary roots, and they are on imaginary line. So that means they are marginally stable. They are not on right hand plane, they are not on left hand plane. That means our system is marginally stable. So this is problem number 5. So let's the characteristic equation of closed loop feedback system be s to the power 4 plus 2s cube plus 4 plus k s square plus 9s plus 25. So first we construct the Routh array s to the power 4. So the first term will be 1, the second term is 4 plus k, the third term is 25. Okay, similarly for s cube it is 2, then 9. So we get k minus half. Here 25. Just after calculating, we will find out that this term is 19k minus 109 by 2k minus 1, and this will be 25. Now if we want the system to be stable, so let's find out what will be the range. So what will be the range of k? of system to be stable. So for stability, what we know that all terms should be positive. So k minus half, first condition is k minus half should be positive, means k is greater than half. The second condition is this term will also be positive. So 18k minus 109 by 2k minus 1 is greater than 0. That implies k is greater than 109 by 18. Now definitely this term is greater than half. So the system will be stable when the value of k is greater than this. So system is stable for k greater than 109 by 18. Problem if we just give a parameter to the system and we tune it and find out how the parameters, what will be the range of parameters such that the system will be stable or marginally stable or unstable. So we consider another example like that. So the characteristic equation s to the s cube plus ks square plus k minus 3s plus 4 is equals to 0. So we have to find out what will be the range of k, so that system to be stable and marginally stable. So we will create its Routh array first. So it's s to the power cube, s to the power squares, then I am taking the coefficient, it is 1, it is k minus 3, then it is k and 4. Okay, so now I'm just calculating it. It is k into k minus 3 minus 4 divided by k, and this is 4. Okay, so stability, the condition will be the system to be stable first. So all the element of first column should be positive or of same sign. So this would be positive here. Okay, so k will be greater than 0. First condition, k is positive. Second condition, k square minus 3k minus 4 by k is greater than 0. So k is positive and it implies k square minus 3k minus 4 is greater than 0. So k minus 4k plus 1 is greater than 0. So we find that k is greater than 4. K can't be greater than minus 1 because here it has to satisfy k is greater than 0. So here we find that if I draw a real line, this is 0, this is my minus 1, this is my 4. Okay, so first condition is telling k should be greater than 0. Second is telling k should be greater than minus 1, and final it is telling k should be greater than 4. So combination of all three is that k should be greater than 4. So we find that k is greater than 4 because k can't be greater than minus 1 because the condition is between minus 1 and 0. So it doesn't holds the first condition. So k should be greater than 4. The system will be stable. So part A is done. Now part B. So we know now we do part 2. So marginally stable. So this term will be 0. If I am considering this term to be 0, so this row will be 0, and when entire row is 0, so I will take the auxiliary equation, that is S4, it will be 4s square plus 4. Okay, I'm just writing it. I'm just writing k, it should be equals to 0, then I will calculate the value of k and then I will put the value over here. That is my auxiliary equation. Okay, from here we will get k is equals to 4, and then I am putting 4 s square plus 4. Then I will take differentiation of auxiliary equation with respect to ds. Okay, that is 8s plus 1. Okay, so that will give me the element of this 8, and then this will be 4. Okay, so now we find that all the sign elements are positive for the first column, because this is 4, if you will see, this is 8, this is again 4, so all the elements are positive of same size. There are no roots in right hand plane, and the roots of auxiliary equation, if you will see, we will take the common term as 4 and I am equating to 0. So there are two roots of imaginary x's plus and minus j. Hence the system is marginally stable with oscillatory frequency of omega equals to 1. How it's omega equals to 1? Because s is sigma plus j omega. So omega value is 1 from here. So system is stable with oscillatory at frequency of omega equals to 1 radian per second. So k is 4 for this. Okay. So the problem 7, we find the number of roots which are in left of axis s equals to minus 1. So how to do that? So we have to find out how many roots are there in the left of s plane, s equals to minus 1. So we consider a dummy variable Sn such that Sn is equals to s plus 1. Now if we replace, we write the characteristic equation in terms of Sn. So it will be Sn minus 1 cube plus 4 Sn minus square plus 6 Sn minus 1 plus 4 is equals to 0. So when I solve it, I will get this equation. Okay, so you find the characteristic equation in terms of Sn to s to the power Sn cube plus Sn square plus Sn plus 1 is equals to 0. Now the Routh array of the system, the Routh array of new equation is Sn cube, Sn square, Sn1, Sn0. Okay, I am writing its coefficient 1, then 1, then 1 and 1, because all the coefficients are 1. So all the elements of first column, if you will see, if I multiply, it will be 1 minus 1 is, this will be 0. So this will be my auxiliary equation, because the row is 0. So it will give me auxiliary equation. From higher term I will get Sn square plus 1 is equals to 0. I am differentiating it with respect to s, so I will get 2Sn. So this is 2, this is 1. So all the elements of first columns are positive. So there is no root on the right hand side of s equals to minus 1. So it is no root s is equals to minus 1, no root on the right of s equals to minus 1. And for the auxiliary equation, if we find the roots, so we get Sn square plus 1 is equals to 0. So Sn is equals to plus minus j. So what we get here is there are two marginal imaginary roots on Sn is equals to Sn. So imaginary axis to be shifted on Sn now. So Sn is plus, this is omega. Okay, so there will be two roots. Okay, so if we will plot it, now if we see the entire picture in S plane, so that is not in S plane. Here we are just assuming that this is S plane. We are going to find out, this is our original sigma, this is omega. Okay, original. So we will shift our axis to minus 1 over here, minus 1. Okay, and there are two roots at minus 1, two roots at minus 1. There are two roots, that is, this is plus j, this is minus j. This is for Sn, this, because we have shifted our axis now. Okay, so these are my two roots. Okay, so if you will see, this kind of excess shift is very useful in phase system where there are number of imaginary or complex root. So more than one complex pair of root are there. So if we are drawing to determine the relative stability of the system based on how the root effect on the damping of system, so the excess shift method using Routh-Hurwitz criteria will be helpful. And the final problem for today's lecture is, now let us consider the same problem what we did in time response. So this is error. So this is that problem for time response where we found if the steady state error is going to be 0, but not for ramp input. Okay, so each will be 1. This feedback is 1. So we can modify loop gain as gs is equals to k s plus 2 by this, over there it was h, so h is equals to 1 over here. So this is my system gain, and the characteristic equation will form from 1 plus gs. So the numerator will give me my characteristic equation. Okay, so the characteristic equation of the system will be the numerator term, and you have to find out what will be the range of k so that the system is stable. Okay, so for that we will calculate Routh's error for this characteristic equation, Routh error table. So it is, if you will see an earlier slide, it's for s to the power 4 it's 1, then 51, then 2, and over here it is 11 and 41 plus k. So from that we are just making this Routh error. I'm calculating another terms. Okay, so this will be 520 minus k by 11, and this will be minus k square plus 2, 37k plus 21, 520 minus k. So we will calculate all the terms. So now we have to find out the value of k for which the system is stable. So there are 3 terms related to k, 1, 2, 3. In the first column there are 3 terms. Okay, so the first condition will be 152 minus k by 11 should be greater than 0. That implies k is less than 520. Okay, second condition is minus k square plus 237k plus 21 by 520 minus k. This is it's 320 is also there. Okay, so this is less than this is greater than 0. Okay, so for that I will put my numerator is equals to 0. I will calculate the value of k. So these are my 2 square roots. Okay, so limit of k will be in between these 2 square roots. So we consider quadratic equation. Okay, then we calculated k square minus k square plus 237k plus 320 is equals to 0. So the root of equations is 237 plus minus, just we can calculate this divided by 2. Okay, so if the term is going to be greater than 0, this term is going to be greater than 0, so we need that k should be lies between plus 237 plus root by 2, and this is upper limit, this is my lower limit. So from here I'm calculating my upper limit is 367. So here it was less than 520, now it is 367. Okay, so now upper limit is reduced to 367. The third condition is, from the third element 2k should be greater than 0. So k should be greater than 0. So this part is negative. So this part will be replaced by 0. This is negative. So this part will be replaced by 0, and the range of k is now, k should be in between 0 and it should be greater than 0 and less than 367. Within this range, the system will be, the entire closed loop feedback system will be stable. Okay, that is it. So thank you. That's all for today's lecture.